Can you hear me, Dr. Abhinav? Okay. Oh,
Yes, I can hear you.
okay, very good. Okay. Okay, so nice to see you. Okay. Okay, so let me welcome all of you to this important talk, which is a part of a celebration of this year's International Year of Quantum. And it's really my honor to introduce Dr. Abhinav Kandala from IBM. Just a few words about his background, I mean, the educational background. He did his BTech in engineering physics. I think it was probably in 2008. And after that, he did his PhD in quantum materials. That was at Pennsylvania State University under Professor Nitin Samat. Yes. And since that time, he's been after completing his PhD in Penn State, he went to IBM first as a postdoc. And I think many of you know his landmark paper in Nature in 2017 on the variational quantum eigensolver. And I think soon after that, he was actually a postdoc at that time. And soon after that, he became a staff scientist and is currently a principal research scientist and leads the IBM team on quantum capabilities and demonstrations. And he's gone on to do a variety of outstanding works on quantum utility, among other things. And I think we're going to hear some of that and maybe other things. And he's the recipient of MIT Tech Review's award for scientists under 35 years of age. And I, like many of you, consider him to be, one of the world's leaders in quantum computing currently. And I should also say that his father, the late Professor K.V.R. Chari, was one of India's, and I think internationally renowned chemist in the field of nuclear magnetic resonance. And he was the first director of ISET Berhampur. And some of you might remember Dr. Abhinav's talk about a year and a half ago when we had a sort of a symposium on superconducting quantum computing. And I think I would like to request Dr. Abhinav to visit us at our center in Kolkata, and we'll be absolutely delighted to have you here. And with these few words, I would now like to request Dr. Abhinav to give his talk.
Thank you so much for the very gracious introduction, also for the invitation. And I'm sorry for the challenges in logging on. So I really appreciate all of your patience. Thanks again, also to Dr. Roy for the kind invitation to this series. And I hope very soon I'm back in India again and able to visit and perhaps do something like this in person and meet all of you. But in the meantime, I think I think we should try and share some of where this technology is, where the science is, and hopefully create some opportunities for sharing ideas and so on. So maybe just right before I start, if there are questions, do we want people to just freely interrupt, or should I be looking out for some chat window anywhere, or is there a preferred mode with this that you would?
Dr. Kandala, I'm Dr. Roy here. So um, uh, maybe we'll ask questions at the end of your talk, if that's
Okay,
okay. Yeah,
sure.
and if there are any questions online, somebody asking over the chat window, we'll also ask you to answer them.
Okay,
So
great.
that's fine. Yeah, thank you. Thank you.
Perfect, perfect. Yeah. So, yeah. So today I'm going to talk about, accurate quantum computing, how we can do um, computing in some trustworthy way, even with this novel paradigm. But at the highest level, maybe I want to also start with, like, do we need new computers? Do we need faster computers? What is the motivation for all of this, right? It's this is obviously an image that's representative of Moore's law, and indicating how the number of transistors have doubled and the power of our classical computers have doubled over the last several decades. And at least while growing up, this was during for me, it was the period of new and new Pentium chips. And I would often wonder, like, why do we need a new Pentium processor? For the tasks that I was involved in on a day-to-day basis, be it like using some chat or email to communicate with my friends, uh, or if it was for streaming something or watching a movie, it didn't dramatically seem to change when these processors got a little more complicated or a little more powerful. Um, and so this was always a question for, like, why do we even need to build new, more powerful computers? And I think if we didn't have this almost maniacal obsession as a society to keep building more and more powerful computational tools, um, I think a lot of what uh, as a civilization we've achieved these days with our smartphones or chat GPT and these kinds of other amazing tools just wouldn't have been possible, right? And it's so hard to have predicted that all of this would have been enabled by building more powerful computers. So we almost built things before we even knew what we could do with them. And I think we're very good at being very creative with building more powerful computational tools, but then along the way also figuring out what to do with them. So I'm certainly a very strong believer in the build it and they will come, right? Like, once we build these more powerful tools, and this extends to even quantum computing, right? We're trying to almost, I'd say, build something before we exactly know what this is going to be able to do. And we have, that said, we have some sense of what these could do, particularly in the context of, say, quantum simulation, where we know there are problems that classical computers could struggle with, right? So one classic problem is in the context of, you know, evaluating or calculating the dissociation energy for a molecule, right? So in this very simple example, if I have two atoms that are very close to each other, uh, they're in a high energy state that's going to be unstable. If I pull them apart very far, they're going to be in a dissociation state and they aren't going to be interacting. But there'll be some sweet spot in the middle where they're at the perfect distance. This is the bond distance, and that's going to be the lowest energy equilibrium configuration. And then one can ask, oh, what's the energy required to break the bond, to 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 uh, to dissociate the molecule? And this is an energy that affects what are called chemical reaction rates. Okay, and these chemical reaction rates are going to be exponentially sensitive to the energy that is calculated or estimated. So one wants a very, very accurate um, estimation of this energy, right? Um, and how would one have access to this, right? This is typically by solving the electronic structure problem. You would try expressing the Schrodinger equation, something like this. And if you look at the matrix representation, uh, this is what trying to evaluate this would look like. And then if you had about n spin orbitals, the task essentially gets down to diagonalizing a 2 to the n by 2 to the n matrix, which, for obvious reasons, is going to get very expensive very quickly. Even at the size of n equals to 60, doing an exact diagonalization is going to be very hard. Okay, and despite the great success of quantum mechanics, this is something that was very well known, even in the very early days. So this was something Dirac pointed out, saying that the underlying physical laws are completely known, but the difficulty is that in the exact application of these equations, the Schrodinger equation, for instance, becomes much too complicated to be soluble. And therefore, it becomes desirable that approximate practical methods should be developed. Okay, and this is exactly how the last century is basically played out. A lot of the successes we've had with quantum mechanics, a lot of the success we've had in predicting properties of materials and other quantum systems comes down to our success with developing approximate practical methods. Okay, and approximate practical methods where an exact application of an exact solution to the Schrodinger equation is not possible, right? So, a natural question here is when you're at these sizes, when these exact solutions are no longer possible, and you only have approximate classical methods to rely on, how do you know if your result is accurate? How do you have trust in your computation, right? So then it's useful to just ask, okay, so what do these classical computational scientists do? How do they actually what's the game that they play to build trust in their methods? So the one thing you can obviously do is you can start out with a simulation of your system at a smaller size, where exact diagonalization is accessible. Perhaps you could also look for interesting special points where you have analytical solutions. And then you can test out your classical approximation at these sizes, at these particular special points, and see, okay, is my classical method capturing the right answer, right? Now, in the history of development of many of these methods, you can start with some well-established classical approximations, and now if you have a new iteration or a new method, you can also try and compare method A to method B and say, okay, well, method A is producing the same result as method B, maybe more efficiently. And since I trust method A's result, I also trust method B. Again, this is perhaps one more thing one could do. The other thing people also do is they can try and systematically increase some computational resource, how much memory they're using, what the runtime is. Very often for methods like tensor network methods, this translates to, for instance, the bond dimension. And then you can ask, oh, okay, as I sweep my classical simulation as a function of this computational resource, am I converging towards the right answer? And that is often used as one test of trust or confidence in the result. But that said, even for these kinds of tests like convergence, you just don't know a priori if that convergence is getting you to converge to the right result. It's entirely possible that you can converge to the completely wrong result, right? And this really is a very uncomfortable game where we're trying to have trust and belief in approximate classical methods, even though we don't know what the exact result is. Okay? But even without that, we're able to place some trust and have belief in these methods, and these have been shown to be very, very successful for a very large number of problems, right? Now, the question is, can you now play this game with a quantum computer, right? Can you now begin to use quantum computers at scales where you don't have these exact solutions from exact diagonalization, where all you would have left are these classical approximations, right? So there are probably two ingredients to this, right? One is you need these devices to be, the quantum computing devices, to be at least at the scale that's beyond brute force classical simulation, right? I mean, if not, why wouldn't you just do the brute force computation? Two, you need the device to produce trustworthy solutions, right? There has to be a reason for you to trust the computation that comes from the quantum computer. Now, the challenge with this is that the error rates on the quantum computers are about 20 orders of magnitude larger or even more than the fundamental building blocks on a classical computer, right? So they're much more error prone than our classical computing devices. So when the errors are so much larger, can one do anything that is accurate or trustworthy or something you can have confidence with on the quantum device, right? So this was also a problem that was very well known, that we were for sure going to encounter, and hence came along, the beautiful theory of quantum error correction, which involves encoding your quantum information into a much larger network of qubits and building some robustness to local perturbations and so on. But the typical challenge with this is you need to have the ability, or you need to demonstrate the capability of being able to uh, to encode information in this very large network of qubits. You have to build these networks, and there are lots of ideas, including at IBM, on how to do this. But this is a very, very challenging um, experimental task, and this is going to be one of the greatest, I think, scientific challenges of our lifetime, to be able to build a large scale fault tolerant quantum computer. This does not exist today, but this is something our group and several groups around the world are very much focused on trying to build. Okay, right. So this is not something we have immediately. Um, so then the question is there a way with our current noisy devices, without error correction, that we can already produce trustworthy solutions, right? So let's try and again do a very quick calculation. This is something I often use to offer some intuition for the game we're trying to play. So let's imagine that we had a quantum circuit with about 100 qubits, and we want to involve 10,000 gates in this circuit. And each of these 2-qubit gates were at the 3 nines level. So the accuracy, the fidelity of these 2-qubit gates is at 99.9%. So if we look at trying to run a circuit with 10,000 of these, well, then the state is going to have a very lousy fidelity for about 5e minus 4. Okay. So the question is now, if the state is this noisy, or the state fidelity is so low compared to the ideal state, is there anything accurate one can do with these kinds of states, right? And the task of trying to preserve the fidelity of this quantum state, that's what quantum error correction sets out to do. But are there other things that one could do, right? And then this is yet another example I really like to point to, is imagine that you had about 1,000 spins, and all of these were aligned, in the same direction, these spins. And if you flipped one of them, right, then the fidelity immediately crashes, the overlap of these two states. But instead, if you asked what was the global magnetization, right, then with this singular flip, that global magnetization is only going to be off in the third digit. So you're actually getting a fairly accurate estimation of the global magnetization. So even though the fidelity was dramatically corrupted, there might be some other quantities, some other observables like this global magnetization, that we can hope to actually extract useful information from, if we haven't corrupted the state too much, right? So in the context of looking at this for a quantum circuit, we have a certain number of qubits, we have gates that we're applying over time, and this is the ideal quantum circuit. What of course is happening though is that over time, because one doesn't have active error correction in this, trying to run a circuit like this on a current device, you're going to keep accumulating more and more noise. So this fuzziness is meant to represent some of that. And then your observable is also going to get corrupted as a result of that. But very much like in the analogy of those 1,000 spins, the idea is, if this if the depth of the circuit, what I mean by that is the number of these blue entangling blocks, is not too much compared to the decoherence times, then you could probably have some signal that you could play with that would not be as dramatically corrupted as the fidelity of the state that you have at the end of your circuit. Okay, this is the question we're trying to ask. And so in this 2017 work, this was something basically that we tried to do. We tried to estimate, with these kinds of short depth, very small, 4-qubit depth 2 circuits even, um, can one do a fairly good simulation of the energies of lithium hydride, okay, which is a problem we mapped onto 4 qubits. And because this is a trivial 4-qubit problem, we know by exact diagonalization what the result is, and now we have the ability to compare and ask, does the quantum computer produce a trustworthy, accurate solution, right? And the answer is a resounding no. This is a huge error in the context of what any quantum chemist might care about. Okay? They're talking of relevant energy scales of millihartree, and this is basically because those chemical reaction rates are exponentially sensitive to these estimates, and the errors here are probably 2 orders of magnitude larger, and something that no chemist worth his salt would think is a worthy result. Okay, but this was the state of what we could do in 2017, even with these very short depth, small qubit circuits, right? And then came along, the invention of a bunch of methods that are referred to collectively as quantum error mitigation. And so these were methods invented by my colleagues at IBM, but also simultaneously at the University of Oxford in Simon Benjamin's group. And the basic idea here is there a way for us to characterize quantum noise in our devices? Once we have access to that, can we manipulate this noise, and then do something to undo its effect? Okay, and this idea should not seem too strange or too alien to us. This is a fairly regular piece in a lot of our day-to-day electronics. Our noise canceling headphones, even our cell phones or laptops have some elements of this kind of active noise cancellation. So this is the basic idea. Of course, the task of characterizing noise on a large device is highly non-trivial, and once again, in general, that's also going to be an exponentially challenging task. But then there are tricks one can do. Okay, so just to give you a sense of how this could be done in practice, I'm going to just refer to this very simple 1-qubit example where we have some noisy circuit, U, and that's expressed by this tilde, and we want some expectation value A that we want to measure, and this is going to be the noisy version of it. So we can model this as the ideal unitary followed by some noise channel. Okay, and let's say that we have sorry, one second. Trying to hide my and let's say that we wanted to precisely manipulate the noise in a way that we want to amplify its effect by a factor of 2. So the way this would be done is modeled is by inserting one more noise channel in there. And now let's say that we've characterized the noise channel, and so we know exactly what the noise process is. This is a bit flip polynoise channel where we know these probabilities P, with which the bit flips, and probability 1 minus P where nothing happens. And now basically if you go and insert this in your expression here by linearity, what you'll see is the sum of 2 terms, right? You have one term with probability 1 minus P and another term with probability P. And essentially what this amounts to is to access your expectation value at this amplified noise strength of G equals to 2, which is basically twice the noise strength. You can access that by running 2 kinds of circuits. One where you've taken your noisy evolution and then just done an identity, and you sample these circuits with probability 1 minus P, and then you take your noisy unitary, and then you slap an X gate, and then you sample these circuits with probability P. And if you averaged over the expectation value that you got from these two, you would now have access to the expectation value at this amplified noise strength. Okay, and now I'll very soon come to what one can do with this, but I just want to say that although I specifically chose the example of amplifying by a factor of two, there's actually a lot of freedom in choosing what this amplification factor could be. Similarly, I chose an example of a very simple poly channel in a 1-qubit case, but then there's a lot of work that goes into learning and characterizing noise channels on large multi-qubit circuits. And I'll skip over those details for now, but perhaps you can take a leap of faith with me and just trust that that is possible to some extent. Right. So as I said, in addition to just trying to amplify the noise by a factor of two, that there are a range of those Gs that you can imagine. You can also imagine canceling the noise. And this is very powerful because essentially, the computation that you would have then would be something that's noiseless in effect. And so if you expressed the inverse of this noise channel, this isn't going to be physical, but if you just engage with me for a few moments, you can express this now as a quasi probability distribution. So you have some normalization factor that gets you gamma, and you have this negative sign, which basically means that when you try and average over these two circuits, one where you just have the identity, and the other where you insert the X gates, like in the previous example, when you're trying to do the average, you basically keep track of the signs. Okay, but also the note here is you now have this prefactor gamma, which is basically going to lead to a sampling overhead. Okay, and it's going to lead to a sampling overhead that's going to be larger as P gets larger. In the limit of P going to zero, that is zero error, this gamma is going to be increasingly close to one, right? So now if you had, instead of just one gate that you want to invert the noise on, if you had L gates, this basically is going to be a sampling overhead to suppress the variance from this gamma that goes exponentially in the circuit volume, right? And really the game of these kinds of methods is we want to drive P towards smaller and smaller values, so that the base of this exponent becomes closer to one, and then even at non-trivial numbers of 2-qubit gates or non-trivial numbers of gates, it's possible to have a manageable overhead. This is basically the game that we're trying to set out with a lot of what we're doing in this pre-fault tolerant regime of quantum computing. Okay, so as I said, I don't want to go into the details of this circuit, but just trust that there is some circuit. The ideal observable is supposed to be one. If I ran this on my noisy device, I get the green point. This is at the base noise level, and then there's going to be some bias compared to where the ideal result should be. But similar to the example that I just showed you, one can potentially try and amplify this noise. Here it's amplified by a factor of 1.2 for the yellow circle and then 1.6 for the red circle. And basically, you have increasing amounts of bias as the noise increases. But now by having these values, these different noise rates, you can use those to try and extrapolate to what the result would have been in the absence of noise. And the different extrapolation functions one can do. Here we try an exponential extrapolation, which is also proposed by Simon Benjamin's group at Oxford, and that seems to do very well. Right? So this is a technique that's referred to as zero noise extrapolation, where we measure at different noise strengths and then try and extrapolate to the zero noise limit. Right? So this was, when these methods were first developed, there was a version of this that we tried, again in our 4-qubit lithium hydride simulation. And here now, by measuring these different noise rates, you could extrapolate, and now these white circles are much closer to where the exact results should have been, right? So this is certainly progress and begins to show a path towards what one can do with existing noisy devices, right? But the question is, these were still on 4 qubits, right? And so, coming back to the criteria that we need to satisfy for these machines to have, some utility is one, once again, you need the qubit counts to be at least at scales beyond what one can do with brute force. So 4 qubits does not cut it. One really wants to be at least at the 60, 70 qubit level, right? And even once you have machines at the scale, you need to show that the machine, the quantum computing device, can actually produce trustworthy, accurate solutions, right? And once you have that, then you can begin to play the game that computational scientists, have been playing for decades with classical approximations. So to satisfy the first bit, we've certainly made a lot of progress on that front. We've also built devices with over 1,000 qubits now. So certainly we've gone well beyond the scale of brute force classical simulation or exact diagonalization. And now part two is we've showed on 4 qubits that you can produce trustworthy solutions, maybe even with these noisy devices. How do you do it at this larger scale beyond brute force? And this gets me to this quantum utility experiment, which was an experiment on 127 qubits. And essentially, the question we were asking here is, if we have a network of spins that share the topology of the qubits on the quantum hardware, for instance, how does the magnetization of this interacting spin system evolve in the presence of an external magnetic field kick? Okay, so we were looking at for the experts in the room, we were looking at some trotterized time evolution for an interacting transverse field Ising model. And these were experiments now at 127 qubits, once again, at a scale beyond classical simulation, beyond brute force classical simulation. Sorry. And the question is, how do you place trust in the result? As I pointed out to the classical simulation playbook, there could be some special points, for instance, the 0 and pi/2 point here, when we're sweeping the single qubit gate angles, which are basically representative of the strength of the external magnetic field kick. At these special points, we know what the right answer should be, and indeed, the quantum device produces something close to the right answer after error mitigation. So the green circles here are basically the experimental data that we have in the absence of any error mitigation. So this is just the raw noisy curve. We can measure this at a few different noise values. I haven't shown this in this plot, and then extrapolate to what we think is the zero noise limit, and we produce the blue trace. Right? Okay. So at these special points, we could produce a trustworthy solution. Now, what's happening in the middle? And we didn't know this at 127 qubits. And so we approached Professor Mike Gelatel at Berkeley, and Sajant Anand was then the graduate student in the group who really tried to help us understand some of this. And so they attempted to simulate this with some of their leading classical methods. And this is what you get, right? You're now in this regime beyond what one can do with exact diagonalization, and you have two classical approximations, which seem to agree quite well here in the low theta limit, but then at larger theta they diverge from each other, but also from the experimental data points, right? So this is again now we're beginning to play the game that classical simulation folks have been playing for a long time. We didn't know what the right result was, given how much more mature these classical approximations were and how noisy our device was at that time. Even I was far more inclined to believe that the classical approximation was the right thing. But Sajant actually persevered and pushed along, and Andrew Eddins on my team as well. And what they pointed out was, oh well, these are just depth 15 circuits, so they're not too deep. Since we're interested in looking at the magnetization, which is basically the average of single side Z observables, we should actually look at what the light cone for each of these observables is. So what are all the gates and the qubits that actually play a role in the accuracy of the observable? And because this was a sufficiently short depth circuit, if you traced the light cone for these didn't extend beyond, say, 30 to 40 qubits for this particular observable. So what that meant was you could just do an exact diagonalization based on that smaller limited number of qubits and still produce the right result. Okay, and then we were quite amazed to see that if you produced the curve from exact diagonalization accounting for the light cones, the experimental data points actually land bang on top of that trace, and it was quite thrilling for us to see this at 127 qubits. But that said, this was only a trick that was possible because of these specific observables and because the depth was sufficiently small. So the natural thing to do now is let's try and extend the depth even more. So we went up to depth 60, and now these light cones extend to scales where one can't do these kinds of tricks anymore. And so here one doesn't have an exact trace to compare to. You only have classical approximations. So we ran this experiment to as some sort of a Hail Mary and to see what is it that we get. And then there were a number of classical simulation groups which tried to simulate this particular curve soon after, right? And this is now exactly the game that classical simulation scientists have been playing. They run different methods. I've indicated them by different black boxes, and they produce this entire spectrum of values for that particular computation. Okay, and essentially in this mix, you don't know what the exact result is, right? This is exactly the kind of challenge that one has when one operates at these scales beyond exact diagonalization. You're going to have a bunch of different classical approximations like this. How do you know which one is the right result? What I haven't told you, though, is that one of these data points was from the quantum computer. Okay? And it lies within the variance of all of these different methods, which I'm now going to label. So we can finally now begin to play these games, right? Where we're able to compare classical approximations now with data from one more computational tool. Because we have the ability to produce trustworthy results from pre-fault tolerant quantum processors. Okay. At these scales where one can only rely on classical approximations and at scales where you're beyond what you can do in brute force classical simulation. So this was essentially this result on evidence for the utility of quantum computing before fault tolerance that I wanted to set up. And with that, I want to dive into all the things that have been the exciting things that have been going on since that work. I think I'm probably half an hour in. I could pause for a minute for questions if there are any, or I could just keep going. Okay, maybe I'll just keep going, and I think as initially proposed, yeah.
There's a question actually, Dr.
Oh, there is, okay.
Yeah.
Just a short question.
Yeah.
Noisy unitary, you have broken up into an ideal unitary and then lambda.
Yes.
So how do you construct your lambda?
Yes. That's a very nice question. So so there are techniques that are referred to as cycle benchmarking, for instance. So you can the essence of this essentially comes down to trying to do repeated layers or of identity equivalent blocks, and then trying to measure the decay of some poly fidelity. So you can have these identity equivalent blocks, for instance, in the case of single qubit gates, that's very easy. But if you wanted to learn those lambdas on layers of 2 qubit gates, you could basically have 2 back-to-back C0 gates, and then you have many repetitions of this, and then you're going to measure some decay curve, and then fitting to that decay is going to give you the fidelities in a spam-free way. Fidelities are products of fidelities in a spam-free way. So that is what we use to actually estimate these lambdas and the fidelities in it. Another piece of this is also, I spoke of polyfidelities. There's another technique that's referred to as polytwirling, where you can convert an arbitrary noise channel to a poly channel by randomly inserting polygates and then undoing them to have the same logically equivalent block. If you average over many poly randomizations, you can show that you can transform an arbitrary noise channel into a poly channel. This is a very powerful trick that we also do to try and simplify the noise. But even after that, a third very important piece is there have to be some assumptions on the locality of the noise generators and so on. Because without that, then this is going to be an exponentially challenging task to characterize lambda on a large n-qubit system. But this is something we can do. We have tests that our noise models are representative at this 120 plus qubit level. I didn't go into all those details in this talk, but this is something I can once again talk a little more about at the end, if that's useful.
Okay, thank you.
Yeah. Thanks for the great question.
Any other questions? Okay, no. Yeah, Dr. Kandala, maybe you can continue.
Okay, great. Okay, so there are a few different things that have been going on simultaneously. I think one thing that's been very promising to see is, there've been a significant change in the scale of experiments that, even external users of our systems have been using, and this has really ticked off a number of what we call utility scale experiments at these scales beyond what one can do with brute force exact diagonalization. I'm told the number of these experiments now on the archive are over 40 in the last 2 years. That's really a significant shift in how quantum computers are being used today. But also, I think this idea of what one can do with error mitigation, what one can do with quantum computing before fault tolerance. This is now an idea that's been embraced really by the community, and there have been these two very nice perspective results by others in the field on what one can do with these machines and how these kinds of techniques can actually take us towards quantum advantage. So that's also very nice to see an increasing number of folks trying to pursue this. Okay. So the data I showed was from one of our Eagle processors, which was, an earlier device. There's been a significant amount of progress in improving the hardware, the error rates, and also the software tools. And there have also been some additional features, particularly in the context of the software experiments that took, I believe, almost 4 or 5 days can now be done in a few hours. And this is about a 75x speed up in the execution time of the utility experiment. And even the software that goes behind now trying to enable all of this noise learning and noise manipulation and extrapolation and so on. Like this particular run is now at a point where even folks who are essentially software engineers can run this and produce traces. And this is done routinely now, even internally in the group. And so this also becomes a big part of, how do you enable a much larger number of people who are perhaps domain experts in a particular field to be able to run these kinds of computations without really knowing the details of the device or without really knowing, what goes into those lambda noise models and how error mitigation needs to happen and so on. So you begin to need to have some amount of abstraction from those details, particularly if you want to expand the the base of scientists who want to begin to play with these tools, right? And then we had our improvements in the error rates, as I was pointing out. Our large-scale processors are now called Herons, and essentially the median gate fidelity here, was an improvement of about 5x. And actually, I should have updated this number. The best 2-qubit gates now are actually even below the 0.05% limit, and this is the absolute state of the art across platforms. Even and these are numbers measured on a large device, not even just an individual 2-qubit device. And it really it's very, very exciting to me to show that this is even possible, that these kind of error rates are even possible, right? So a natural question is what do these kinds of improvements in error rates, going from, say, 1% errors to 0.1% errors, what do they enable for error mitigation and the kind of error mitigation sampling overhead one might have? So if you had a 100-qubit circuit with a circuit depth of 100 densely packed layers, this basically translates now to a sampling overhead win of over 70 orders of magnitude. So these are exponentially sensitive to the error rate. So any modest improvement in error rate dramatically enhances what we can do with error mitigation, right? Now, for people who might be familiar with superconducting qubits, one very common challenge with these are what are called defect two-level systems, or TLSs. And these are basically defects that come in resonance with our qubits, and these can lead to fluctuations in the performance of the qubits. They lead to fluctuations in qubit gate times, which translate into fluctuations in gate fidelity. They often mess with certain qubits at certain times and then switch to other qubits. So this really causes some non-uniformity in the device performance, the device throughput, but also in the context of error mitigation. These kinds of defects can lead to noise model instability, right? So ultimately, the accuracy of the error mitigation is going to be strongly linked to how representative or accurate noise model is, those lambdas are. And so in our newest devices, we also have the ability to tune the TLS qubit interaction. We can do these with local electrodes for each qubit. And this is work that you can refer to. This should appear in Nature Communications very soon. But with this kind of tunability, we can really show that for instance, on a metric like T1, this can really be stabilized. So if you were doing nothing, for instance, you have these sharp dropouts. This is just looking at the T1 of a single qubit, right? But with different modes of this TLS control, we can really stabilize the noise, and this translates into stable noise models, is what we show here. Basically, on the y-axis, we're looking at these lambda coefficients, the model fidelities that we measured, and so basically you have these large fluctuations in the noise model as a result of these qubit TLS interactions, which we can really stabilize over the course of for instance 2 days here. And this is a very important ingredient, once again, to be able to produce more accurate results from error mitigation. Okay, so all these hardware improvements, what do they now enable for advances in error mitigation, right? The utility experiment was an example of zero noise extrapolation, but really I think the gold standard, the absolute gold standard for what one can do on noisy devices with error mitigation, for me, is really probabilistic error cancellation. And I briefly alluded to how one can effectively invert those lambdas by sampling once again over these many circuits, but accounting for the signs and accounting for this rescaling factor, which translates into an exponential sampling overhead. And the really powerful aspect of this is there is no extrapolation. If you had a representative noise model, if you correctly inverted the noise in effect, you would basically have unbiased error mitigation. And this is an example on, once again, 50 qubits, where we can show these were on some simple mirror circuits. So we know the results should have been 1, and we can basically show, look at what the unmitigated expectation values are, with signals even going below 1%. And then with this technique, we can show that we can do unbiased mitigation on 300 qubit gate on 300 gates in these 50 qubit circuits, mitigating observable weights of going up to 50. So essentially all the qubits in the device. And this is very powerful because essentially this sampling overhead is completely independent of the circuit and observable complexity. So essentially this is saying you can give me any any circuit with 300 gates and any observable that you might want. And if I could operate this accurately, then I would produce unbiased mitigation, right? And so even an experiment at this scale, it might feel like a small number of 2 qubit gates, but even doing unbiased mitigation at this scale really had to rely on the hardware improvements. This was data on a heron, and we had a factor of about 1 million reduction in sampling overhead compared to if we had to do the same experiment on an Eagle processor. So this wouldn't have been possible basically on an Eagle. And essentially now if we can have the error rates be uniform and drop down to the 1e-3 level, and we know this is possible in practice because we've already shown error rates at the 5e-4 level, we can basically do about 2,500 2 qubit gates, unbiased mitigation on about 2,500 2 qubit gates in the same runtime, which was about a few hours. And that would be very, very powerful to be able to do unbiased error mitigation with also rigorous error bounds, where you can trust the result, right? Now, in addition to all of these, we also have methods that are now integrating classical HPC. And this is once again, in exchange for some bias, you might be willing to accept some amount of bias. You might be able to throw classical resources, like classical runtime. And with that, we're able to now reduce the sampling overhead of methods like probabilistic error cancellation. And this basically means now that by taking help of classical HPC, you can execute larger circuit volumes and do mitigation on them with higher error rates. But what it also means is as the community of classical simulation experts keep developing increasingly novel classical methods, you can actually leverage these and almost do a quantum enhanced version of it that could produce advantages over just the regular classical simulation methods. There are many examples that are in the works, and some of these have been published. I just want to highlight one particular method to give you a flavor of what some of these methods do. This is a method called tensor network error mitigation. This was developed by a Finnish startup, Algorithmic, and we closely collaborate with them. So the idea here is that you have some ideal circuit U and you want to measure some observable O. I could express this as a noisy version of the circuit, followed by the noisy inverse, and then the ideal U once again, right? And then essentially for this block, I could do a tensor network contraction, which is going to change this, which is going to transform this O to an O prime, and essentially the task of measuring O on U, on the ideal circuit U, translates to the task of measuring O prime on U tilde, which is the noisy U that I can implement on the hardware, on the quantum hardware. So now a question that you can ask me is, oh well, if you could do a classical simulation of this, why do you even need a quantum computer, right? But the key idea here is, even if U is very complicated and has very complex dynamics and is hard to simulate, this object in the limit of low noise is very close to an identity, right? So if you did a middle out tensor network contraction, starting out from the middle in here, then you can basically, in the limit of low noise, that classical simulation can be much more accessible than simulating you. And so you can easily imagine these kinds of computations being accessible even when U is hard to simulate. So this was also an experiment that we could do with algorithmic and Trinity College. This is work that should appear in Nature Physics very soon. And once again, it's the same game. How do you build trust in these methods? How do you build trust in the computation? You try and so we looked at certain chaotic models with exact analytical solutions. For the experts in the room, this was work on what are called dual unitary circuits, which are maximally chaotic models. But once again, here you can when you have these analytical solutions, you can compare the result from the quantum computation. It does a very good job. This is at 91 qubits. This is once again beyond brute force diagonalization. And then if you perturb away from these analytical solutions, you get to points where you can only compare to classical approximations. Some perform better than others, and then in those cases, we actually see that the quantum computer is producing what we think are good results. Okay, right. If I could just take maybe like 6 or 7 minutes to wrap up, I want to now get back to the example I started my talk with, the electronic structure problem, right? And so this has been, of course, a very hot topic, often believed to be one of the big killer use cases of quantum computing. Prior to 2014, for instance, people thought that the only way to do this was by quantum phase estimation. That was obviously going to be something that was going to be accessible in the fault-tolerant regime. And then came along the variational quantum eigensolver. This was in 2014. This was basically let's prepare a variational ansatz on the quantum computer, and then do some energy minimization routine to try and see what's the lowest energy that the ansatz produces on the quantum computer. So the first experiment was in 2014. For a few years, we were stuck at about just 2 qubits. Then came along, some of the work that we had done in 2017, extending this to now lithium hydride and beryllium hydride, and so there were algorithmic advances like those that enabled us to get a little larger year by year. But basically, over that last decade, if you saw, the largest electronic structure problems that one could do on quantum computers did not extend beyond 20 qubits. Okay, so all of these demonstrations basically were at scales where one could have done a simple brute force exact diagonalization. So there's going to be no utility to running these on a quantum machine beyond actually learning something about the quantum machine, right? This is basically a table summarizing the scale of electronic structure calculations on quantum computers. And then basically what I want to talk about is the importance of algorithm discovery. So this is now pointing to a new experiment by my colleagues at IBM that have dramatically shown that you can actually do some of these kinds of chemistry problems now at the 80-something qubit level. So if you're interested in the details, this is now work that's appeared in Science Advances. That was actually on the cover there. But this is also on the archive. These are techniques of methods referred to as sample-based quantum diagonalization. Okay, so just to give you a sense of what are these algorithms even doing, once again, it's similar to the example I started out with. You have to essentially solve this eigenvalue problem. We want to diagonalize this matrix, know what the eigenvalues are and the ground states, and basically you have an exponentially large number of these configurations. Okay, Now, the idea is in the true ground state, perhaps one doesn't have all of these exponentially large number of configurations. Maybe there's a subspace that's actually more relevant. And perhaps there is a way to reduce all of these useless basis vectors, right? And now if we had a much smaller subspace, that subspace could potentially be something one can actually perform diagonalization on, right? And this becomes a more tractable eigenvalue problem. So this is actually something that a lot of classical methods do, and the methods that are referred to as selected configuration interaction, which basically try and make guesses for different sets of configurations where you truncate and enlarge and truncate and enlarge and diagonalize at every point these different subspaces, and you try and look for, is the energy dropping over many iterations of this, and there can be challenges with that. The other is, what this novel algorithm is trying to do, the sample-based quantum diagonalization, where you can ask, can you actually execute a circuit that produces samples that are representative of the subspace, and can you use that to identify what the right configuration space is, and then diagonalize on that, right? And basically, this dramatically enhanced the scale of electronic structure calculations. So you have a component here which involves measuring these bit strings, identifying these configurations on the quantum machine, and then there's going to be an HPC component of trying to do this diagonalization. But so with both of these working in tandem now, with 45 qubits for molecules as complicated as Fe2S2, we can basically produce results from the quantum machine that match state-of-the-art DMRG. And this I find completely amazing, that you can already be at this boundary of what one can do with exact diagonalization, and really match classical state-of-the-art, even on existing noisy devices, right? And then this experiment was pushed even further to Fe4S4, and here you basically see that the experimental results outperform some classical approximations, but were not able to beat some others, like the CCST here. But then this is the latest version of this experiment now, where you can beat even CCST. Beating a number of these classical simulation methods goes beyond the 2024 experiment, and of course it's still not quite a DMRG, which is the state of the art, but that you can do electronic structure calculations at this scale, have signal that you get from a quantum device, that you can produce results that beat several other classical approximations, are more trustworthy than several other classical approximations, is really amazing to see, compared to 2017, where we were really just playing around with 4 qubits or 6 qubit experiments, right? And the very nice aspect of this is this algorithm is variational, essentially, right? So you have the luxury of being able to rank the quality of your results. The lower the energy, the better the solution. So if you could find a model or an example where you produce the lowest energy compared to any other known classical estimate, then that would be an example of verifiable quantum advantage, even in the absence of an exact solution, right? That would be an important, a very important milestone. Okay, so I think on my final slide, these are all examples of utility and how to build trust and do computations that we have confidence in on existing pre-fault tolerant devices. We obviously want to take this from utility towards advantage, where you also have a demonstrable superior efficiency, cost effectiveness, or accuracy than what's possible with classical computers alone. But a very, very important aspect of this, to determine that whether you have advantage or not, you need to have trust and belief in the correctness of your output. right? There has to be a way for you to validate. This could be done, for instance, using error mitigation methods like probabilistic error cancellation, where you know you can produce unbiased results, where you can have rigorous error bounds, so you can really have trust in the computation, or things like the sample-based quantum diagonalization, variational approaches like that, where if you produce the lowest energy, then you know that this is the best variational solution, and then you have trust that this is an example of verifiable quantum advantage. So with that, yeah, I think my take-home messages are basically that with existing devices today, we can perform accurate computations at very non-trivial scales. And as one has improvements in the speed and quality of these devices, as we integrate classical HPC and have further research into candidate circuits and algorithms, this will take us very soon from utility to quantum advantage. Okay. With that, thanks for your attention, and I'm very happy to answer any more questions.
Yeah, I mean, thank you for a great talk. Any questions? Yes.
You have shown the picture of reception junctions, and you mentioned about different channels of producing noise, like a strain, TLS, all these things. But do you use in your simulation somewhere the measured noise from those phenomena, from those channels?
It's a great question. The noise model has to be representative of, or has to be inclusive of all these different noise channels. So we don't, it's not possible for the noise model to specifically separate yet that this is coming particularly from the TLSs. Is this a certain noise coming from some control errors or aspects like that? There are ways to separate coherent and incoherent errors, but we're not quite, at least for the incoherent sources of noise, we're not quite separating what the different sources are. But we can have a noise model that encapsulates all of these different mechanisms, and we try and simplify it by this method I was referring to called polytwirling, where we can transform that noise model into a poly channel.
Okay, so that also includes the noise introduced by the microwave pulses that we use to control?
Yes, absolutely. So it includes noise so if you had some additional noise from the microwave pulses, or if you didn't have perfect calibration, and you're instead of applying a theta angle, you insert a theta plus epsilon, and so you have some coherent over or under rotation, it would capture that. If you had some classical crosstalk or microwave crosstalk that's a part of the device design, for instance, it would capture that. So yeah, I mean, so you really need the noise model to be representative of the noise on the device.
Okay, thank you.
Any other question?
Hi.
Hi.
Thanks for your nice talk. I'd like to know that you somehow defined this, you mentioned actually the light cone.
Yes.
Can you define light cone in the context of quantum circuit?
Sure. Probably would have helped for me to have a specific, usually have another slide. Okay, let's talk of this example here. So let's say that this is a 127 qubit circuit, but you're actually measuring only a weight 1 observable. Okay, so if you're measuring just a weight 1 observable, you can start tracing back from the observable, just geometrically, what are all the gates in the circuit that are connected to that observable. Okay, so for instance, what this is supposed to represent is that the entire yellow region represents gates in the circuit where I can geometrically connect to that observable that I was interested in. And everything in the blue, those gates do not have any effect on the observable. So those gates, errors on those gates are not going to impact the accuracy of the observable and play no role in the computation of that observable. So this is called the light cone, the light cone of information. So what are all the gates which impact the quantity we're trying to measure? And then in the context of trying to produce an exact trace for this 127 qubit experiment, the point I was trying to make was that if the depth is sufficiently small, then this light cone doesn't quite have the opportunity to expand over the entire device. So for certain observables, what you'll see is that the light cone only is going to go up to about 30 or 40 qubits. So only the gates in this yellow cone are going to impact the observable. None of the blue ones are. So when you want to do a classical simulation, you can only do a classical simulation with these qubits in the light cone. Does that help clarify?
Yes. So it's about
Yes.
backward light cone, right? So
Exactly.
okay. Thank you.
Okay, any other questions? Comments? Oh,
Hello. So thank you, sir, for giving me this, giving us this beautiful talk. So I wanted to ask about the when we place our quantum circuits on the physical devices with respect to their native gate sets. At that time, the number of ECR gate counts rapidly increases due to the adding of more swap gates or something. So in that case, how we can place strategically, in which strategy we have to follow so that the number of ECR gate should be low in that case. One thing
Okay.
is that
Yeah.
we can we can take the good accuracy 2 qubit gates on the physical device, but in most of the cases it doesn't work for the devices that are available for the free users. Right?
Mm-hmm. Right. So this is a very nice question. And this is also, once again, I think where circuit compilation and compiled research is going to be very effective in trying to reduce some of that. I do want to say one more thing, that very soon we should have a higher connectivity device. This is called Nighthawk, which is going to be a square lattice instead of the heavy hexagon lattice that we have now for the Herons and the cross-resonance devices. So that in itself will try and simplify or reduce the number of swaps you need for certain problems at least. But also, this is also I also see very interesting examples. People have things that are it's called AQC. I think it's called approximate quantum compilation, for instance. So what you can imagine is if you had a circuit and after compilation onto the native gate set, it gets very long. One can once again play this game of leveraging a little bit of classical HPC or a little bit of classical simulation methods, where you can try and use for instance matrix product state simulation to try and produce at least for part of the circuit, produce a shorter depth block that produces the same fidelity state to a certain amount of accuracy. So this obviously is not a game you can play indefinitely, but you can hope to have some win on at least a fairly short depth part of the circuit where you could do an efficient classical simulation, or where you can do a reasonable classical simulation with something like NPS. So this is also something useful that one can do. There are a few other things, if you're interested in for instance doing something like an icing simulation, and you wanted to do a fractional ZZ gate, then instead of using two C0 cross-resonance gates, you could also do a fractional cross-resonance interaction, and that also would enable the circuit depth to drop by a factor of 2. But anyway, I'm trying to give you an example of how the tricks with hardware, but even with integrating with classical HPC, where one can really use many of these to try and pull down the circuit depth.
Yeah.
Thank you.
Any other question, comments? Okay, so I mean, I have a lot of questions, but I'll just ask one.
Okay, sure.
Yeah, about this, quantum-centric supercomputing.
Uh-huh.
Yeah. So, are you aware of quantum algorithms for diagonalizing large matrices? If there are such algorithms, I mean, I know of a few, of course, not too many. Then the whole thing can be done, on a quantum computer, both the selection of configurations and the diagonalization of the Hamiltonian in that selected configuration basis. So the question is, are you aware of, efficient, algorithms, quantum algorithms for diagonalizing large matrices?
Oh, I see. So you're asking in the current form of the algorithm that I showed, the diagonalization happens on classical HPC, but you're asking could one do the diagonalization directly on the quantum device itself?
Yes,
Is
yes.
that
Yes,
the
yes.
question? I'm not too aware, would be my short answer. But what I could say is that doing the diagonalization on the classical HPC is very attractive in the context of it having already some noise resilience. And to give you a very simple example of that, sorry, just quickly. Yeah, to give you a very simple example of that, when I'm trying to do this diagonalization, it doesn't necessarily depend on whether this circuit is producing the exact state. It only relies on having to have support bit strings on the right configuration, right?
Yes.
So that is a very powerful way of inbuilt error resilience, where you can have severely damped amplitudes in some of these by noise, but if you had support on that bit string, then you can still produce a very accurate result. So this is I think a very attractive way of trying to produce fairly competitive solutions even on existing noisy devices. What kind of noise resilience or error mitigation would need to be done if this diagonalization had to be done on the quantum computer itself? That's something I'll need to look into some details of how these are being proposed. But yeah, if you have references, I'd love to take a look.
Okay, yeah, very good. Okay, thanks a lot. Let's see, any other questions?
Okay.
Okay.
Thank you so much for all the wonderful questions. Yeah.
Oh, thank you so much for this outstanding talk, and hope to get in touch with you again sometime. And again, do visit us when you're in India next time. Okay.
Absolutely.
Okay. Thanks.
Thank you so much, everyone.
Thanks.
Thanks so much.